for section 2.2, I kind of thought it would be good to put these two problems, number 25 and number 15, next to each other, because they're different, yet you can use the same things for them. And they're kind of unique, each one. So on problem number 15, this is a homogeneous equation. Differential equation. And the reason why I know that to be true is if I were to substitute something like yt everywhere I see a y and xt everywhere I see an x, and do that too here, I'm going to see that I end up with like a t squared times y squared plus xy. And I'm going to end up with like a t squared times x squared here. And so what I see is I end up with the same equation, but just multiplied by t squared. So that makes this a homogeneous differential equation of degree 2. And so it's good to solve it by substitution. It's just like what substitution would be best. And when I'm looking through it right now, because it's not separable, you've got, x and y kind of buried within the dx there. You're not going to be able to use separable. You're going to have to use some sort of a substitution. And when I'm looking at it, I could choose to divide every term by x squared. And if I do that, I'm going to end up with y over x, the quantity squared, plus y over x not squared dx, and then minus 1 dy equals 0. And so if I were to let v be y over x, so that y is vx, my dy then is just v prime x plus d plus just v. And so that quantity is what would go in place right here for dy. And then I could put v's in each of these. And because this quantity is the messy one, it's kind of better to have it here being multiplied by 1 instead of to work with a substitution that was going to make me substitute something in for dx that would be ugly. So it really is the best substitution to use some sort of new letter equals y over x in this case. Now, problem number 25 is not a homogeneous differential equation, and that's because of this exponential here. It isn't going to be the case that if you nested in xt where you see x and yt where you see y, that it's going to be simplifiable to this t that can be removed. So it is not a homogeneous differential equation, but that doesn't mean you can't solve it with a substitution. However, the substitution that might be best to use is really more evident when you look at the exponent here than anything. It actually, in this case, would be better to make the substitution of, I'm going to use some new letter, I'm going to use u is equal to x over y instead of v, just to emphasize that it would be a different substitution. This substitution would be better because of what I see in that exponential position right there. In addition, then I'm going to know that x is equal to uy, and so therefore for dx over dy is going to be u prime y plus u by product rule. So that's what I'm going to substitute in here for dx over dy, which is another indication that this substitution is really the best one, because what they're asking for is dx over dy instead of dy over dx in this differential equation. I'm not going to do my substitution yet, though, because I've got this x and I've got this y, and I really need to have, for example, everything disappear besides the y's. So I'm really going to want to do something to make sure that this x disappears. So what I'm going to choose to do is divide every term by y first before I start my substitution. So I have 1 dx over dy is equal to that x over y, which I'll be able to substitute out, plus 4 times e to the negative 2x over y. Now when I do my substitutions, I have dx over dy, which I know is equal to u prime y plus u. And I have x over y, which is u, plus 4e to the negative 2u. So remember that u prime is du over dy. And then with the u's on both sides, conveniently, those disappear. And so what I have here is, if I want, I could divide both sides by y, and I have 4y, and multiply by dy, and I'd have dy. And I can multiply both sides by e to the negative 2u, and what I have here is e to the positive 2u. Or I divide both sides by e to the negative 2u, and I have e to the positive 2u du. Integrating both sides, or finding the antiderivative of both sides, and remembering to insert the plus c, is going to give me 1/2 e to the 2u is equal to 4 the natural log of the absolute value of y, and then I'll put my constant of integration right there, plus c. Now, recall that u is equal to x over y, and I don't want u's in my problem, so I substitute that back in. 2x over y is equal to 4 natural log of the absolute value of y plus c, and this implicitly defined equation, family of equations, are solutions to that differential equation. Just to make sure that we have some sort of check of that, I have here the slope field graph for this differential equation. I did have to flip the differential equation over in order to use this sketch. I had to graph dy over dx, not dx over dy. But then when I graph my solution, I can see how that solution kind of flows through that slope field. And this is in a family of solutions, and each for different values of c, we have particular solutions to that differential equation.